Welcome to Lesson 11A, Tunnel Ventilation Introduction. We're going to spend a couple days talking about tunnel ventilation, and I want to start off by saying that of all the things that I wrote in the book and of all the lectures that I give in this class, this is by far my favorite part. We'll typically be talking about automobile tunnels. You have a whole bunch of these cars, maybe some trucks, and they're all moving along a tunnel. And the problem is that each of these guys is putting out some air pollution. There's also air coming through like that, a tunnel that starts at x equals 0 to some length L. We're concerned about the emissions. Typically, CO, carbon monoxide, is of concern because car engines put out a lot of particulate, and they've been cleaned up a lot over the years, but they still put out some CO. The air quality in the tunnel is not of concern for the passengers in the car. However, it is of concern for workers. You don't think about it, but there are workers, especially in these big tunnels. There's people that work in the tunnels, so OSHA gets involved. OSHA has to monitor the air quality in these tunnels. The concentration of CO must be less than the PEL of carbon monoxide or any other chemical, particulate matter or any other chemical that also come out of cars. Also, we must design for the worst case scenarios. For example, accidents, traffic jams. Imagine you're in a traffic jam, and I've been in traffic jams in tunnels, and most people just keep their engine on. You got all these cars close together, everyone's putting out air pollution, and you're wondering, is this stuff safe for me to breathe? So we hope the ventilation system has been designed well enough to handle that. There can be fires when there's accidents, and as I already said, tunnel workers. So I want to address these here just briefly because we're going to mostly talk about checking if the levels are less than the PEL for normal operation. But I just want to mention that there are emergency ventilation systems that kick into effect for accidents and fires. But we will examine in detail the day-to-day operation and the kind of ventilation systems that we use for that. By way of introduction, I want to point you to the videos on the course website. There's 3 short clips, and you can find others, but these are ones that I thought were fairly interesting. This first one, they introduce smoke, and they're testing an emergency system. So the first few seconds here, that's the normal ventilation. And now they turn these emergency fans on, and you could see how much faster the air starts blowing. They're testing an emergency ventilation system for when there's a fire or an accident or something like that.
Lieutenant Croatia. Rush hour traffic backs up in a busy commuter tunnel. In these tight confines is a formula for disaster.
Ouch. Well, that was a pretty bad accident. This one also shows interesting accident.
Which then caused a major pileup involving 4 more trucks.
Wow, pretty bad accidents. We're going to look at 4 different types of tunnel ventilation, and I'm going to concentrate mostly on the last one. And for all of these, we will consider only one-way traffic. There are some older tunnels where you have 2 ways, but all the modern tunnels have different tunnels for each direction of traffic. So we're not going to have cars coming at us. We have all the cars going in the same direction. So what happens is you get some entrained air through the tunnel, even if there's no forced air system at all. So there will be some capital U, which will be the wind speed through the tunnel. The car itself is traveling at some speed VC. And of course, there's an emission source from each car. I just draw 1 car here, but there would be several cars going by. This is an unsteady process, but we're going to actually analyze it as a steady process, and I'll show you how to do that in a minute. Again, the tunnel goes from 0 to L, and we're talking here about natural ventilation first, and that means that there's no forced ventilation at all. There's nothing in there. It's just a tube. There's some natural ventilation because of what I said here. There's some entrained air through the tunnel, so you get some capital U. These are a good design for short tunnels And by short, we mean less than about 300 meters. A football field is about 100 meters. So imagine a tunnel less than about 3 football fields is about the limit of where you can use natural ventilation. The problem is that C grows with X. There's no place for the emission to go. So C is some value here, and it will be a different value here, where C2 is greater than C1 because the air's moving and picking up air pollution as it moves along, so that by the time it exits the tunnel, you're going to have a fairly large concentration of CO or whatever other contaminant you're talking about. So that's what limits this to 300 meters. I just want to mention for subways and trains, the problem is the walls are much closer. These are smaller tubes that subways go through. With a car tunnel, you have to have the walls pretty far away or you'd have a lot of accidents. But for subways, they're on a rail and there's no problem with them hitting the walls as long as there's a little bit of clearance. So what happens is this: you have this tunnel, and then I'll draw a train of some kind. It's moving at some VC, and the walls, as I've drawn, are very close together. If it's moving, especially at a high speed, you have a high pressure in front and you have a low pressure behind. And so you're pushing that air. You can think of this subway car as acting like a piston that's pushing the air. We're compressing the air with high pressure. If you didn't have any kind of way to relieve that, you would start really compressing the air and getting higher and higher drag on this car. In the meantime, you're drawing air back here like this. So what they do is they put in relief ducts, shafts that come up. This is all below a sidewalk. So this is a grate. As the subway car is coming close to one of these shafts, it pushes the air up. Meanwhile, air gets sucked in from the sidewalk and travels behind the subway car. These are called pressure relief ducts or shafts. This particular one has air exhausting to the sides, but they can also exhaust up and down like that. So they call it a downcast shaft and an upcast shaft. Of course, as it moves along to the next set, this one will become the down shaft, and the next one along the line will become the up shaft. So if you're standing here, as the car approaches, you would have air going up, and then once the car passes you, you would feel the air going down. Here's a typical subway grate with leaves. So when the air is sucking in, it sucks the leaves like that, and they tend to coagulate there. And then when the air is being pushed up, it'll blow those up. And the famous picture, of course, is Marilyn Monroe. In this case, there was air blowing up from the subway down below. I believe this was in New York City, and it's a famous, iconic picture. And this is the sidewalk grate. So next time you're in a city that has a subway, find one of these grates and stand on it. And when you hear the subway start to come, feel the air blowing up. And then if you wait till the subway passes, and you'll hear it down below, and then you'll feel the suction going back down. You won't really feel that too well because of the candle effect, which I will describe in a couple lectures. So that's natural ventilation. If it's a longer tunnel, what do you do? The next more in complexity is what's called local makeup air ventilation. And that is when you blow in some air, and we call that makeup air. Just like we do in rooms, you blow in some fresh air from outside, and you blow it kind of in the same direction as the traffic. Local means it's at one location, and it's usually right near the beginning of the tunnel. Again, you have this entrained air. So as you're approaching the tunnel, if this is x equals 0 right at the beginning, and this is x equal L at the end, you have some air that's naturally coming through like the natural ventilation, but then we're adding some more air. So what that does is make the U increase. And once it increases here, it'll stay constant after the makeup air is added. These can be longer than natural ventilation because we've added some air to it, about twice as long. So these can go up to about 600 meters. And remember, for the natural case, they can only go up to about 300 meters. We said at that time C goes up with X. Well, we haven't changed any of that. We still have C rising with X, but more slowly than the natural ventilation case A. Again, there's no place for this contaminant to go. Once we emit it, it has to go downstream, but it's just a higher velocity. And so if I plot C as a function of X, for the natural ventilation case, our C would go up linearly In reality, it's going to veer from that a little bit, and that difference is due to wall losses. Wall losses is a little bit of a sink, especially for particles. These particles can settle on the ground, or they can be trapped on the little ridges and stuff on the walls. Those walls get dirty, and you're losing some of your contaminant naturally through wall losses. So we'll include that in our analysis. We would expect for this local makeup air case that it would be still growing linearly, but not as fast. And again, there'd be some wall losses. That's why we can make these tunnels longer. The problem is that U can get too large, and that causes instability in driving. So imagine driving through a tunnel. Even though the air is moving with you, if that air is moving at a pretty good clip, you're going at 60 miles an hour and the air is coming at 30 miles an hour, it's going to be an unstable situation. Your car's not behaving the way it should when there's a wind like that. You don't want to be pushed around inside a tunnel. We can say that the bigger L, the more makeup air is required to keep C at L less than the PEL for whatever contaminant you're talking about. If we have some concentration at the PEL, this would be L max for a natural case, whereas this would be L max for the local makeup air case. Anything beyond that, for L greater than approximately 600 meters, you need some kind of distributed ventilation system. Instead of just at one place, we have to put in makeup air in through a whole bunch of slots in the ceiling, for example. So that'll bring us to C, which is uniform makeup air ventilation, no exhaust. This is also called no exhaust ventilation. What we're doing is still adding QM, except instead of adding at one place, we're distributing it through the whole tunnel. And we do this through slots, typically either in the ceiling or along the sides. I can't draw sides here because that would be in and out of the page. So we're going to draw that as coming from the top. You have some naturally entrained U naught here, but we keep adding some flow, and that gets added to the air. So the capital U is up as X up. At X equals 0, we have a small air speed, and then the air speed increases with X. And so you have that maximum speed here because you keep injecting all this fresh air. This ventilation is good for L less than approximately 1,500 meters. And if I plot U as a function of X, it's pretty much a straight line. And so the problem with this ventilation system is that U can get too big and be dangerous to drive. The good thing is, though, with this system, as far as contaminant, C levels off at some X. There will be some C max, and it turns out to be a first order ODE, and it ends up leveling off.
Then the tunnel can be as long as we want, right?
Yes, for as far as C is concerned, OSHA would be happy about the contaminant. But the problem is the U, if the U gets too big, then you're in trouble because you'll have accidents. But C does level off at some maximum. And then hopefully the PEL is above that so that this would satisfy OSHA. Let's now talk about transverse ventilation, and this is the best one of all. It's the most complicated, but it's the best one. And this is the one that we will analyze in detail next time. We moved the QM down as distributed makeup air, but here we also have an exhaust. If I cut off the exhaust, I have the same thing as I had last time. So I'm trying to illustrate here the QM comes down behind this diagram and then out. And I'm drawing it through the road because I can't draw into the page, but these are generally on the side. Now we have both QM, makeup air, like before, and QE, exhaust air. So it's sort of like a room where we have makeup air, we have exhaust air, or supply air, and exhaust air. These are, again, slots typically on the ceiling for the air that's going out. And then we have makeup air through slots on the side walls, generally. L has no limit because once this settles down, it turns out that U of X is equal to U of 0 equal U of L equal constant. By the way, you can have unbalanced, but we're only going to treat the balanced case when QM equal QE. We call this balanced transverse. ventilation. This is actually the only type of ventilation that we're going to analyze. Most of the time, they design these so that you have the balanced transverse ventilation system. You're adding some flow and you're taking out some flow at the same rate so U doesn't change. And also, C of X reaches a maximum at some X. Actually, it's a first order behavior, so it theoretically never reaches a constant. If I plot C as a function of X, there'll be some C max, and you get a first order ODE. C approaches some C max. And then this can go on forever. You can have as long a tunnel as you want. Here's an example. I go to Virginia Beach. This is the famous Hampton Roads Bridge Tunnel. I did not take this picture while I was driving. Please do not ever take a picture while you're driving, especially through a tunnel. These are the slots for the QE, the exhaust. Air is coming up through those slots. And then I had my wife take a picture pointing towards the walls. This is fresh air coming through these slots. This is the makeup air coming in from the side. So next time you go through a tunnel, you can observe these, but be careful if you're driving. I don't want to cause an accident. Let's look at sources and emission factors. We have multiple emission sources from a whole bunch of cars going through here. Here's a transverse ventilation system. We want to look at the total source strength S in this tunnel due to all these cars in there. These cars are moving. So what is S? Well, we're going to use emission factors. And here's the key point here. We analyze, and this is an approximation, as steady state. On average, we say that C, for example, varies only with X, not time. And U is U of X. Of course, if it's balanced, it's a constant. We're going to approximate this as a whole string of cars that are uniformly spaced and they're all moving at the same speed, VC, which is the car speed. So how do we get S? We're going to use this equation, S equal EFC, emission factor per car, milligram per car per kilometer. You can look that up in our tables. Recall that for EFs, the EF denominator is anything appropriate. Here, the denominator is per car per kilometer, milligrams of CO or whatever contaminant per car per kilometer. NC is the traffic density, so the number of cars per kilometer. VC is the car speed, as I already said, and then L is the tunnel length, sometimes given in meters, sometimes kilometers. And VC is often in meters per second or miles per hour, so you always are conscious of units. So what is that EF? In our book, we show the old one, which was about 5,600 milligram per car per kilometer, and this is the newer one. These are both, by the way, for carbon monoxide. So cars have gotten less polluting. This is the one that we'll use for modern cars, or you can use this, figuring there's a lot of old cars still in the tunnel, and use it as kind of a worst case scenario. So I wanted to just first look at the units to make sure this is what we want. We end up with milligrams per hour, which is what we want. It's a source strength mass per time. If you're driving in a tunnel, the traffic density goes up or down with car speed. So typically VC goes down as NC goes up. And those tend to balance each other out. Higher traffic density makes cars slow down. As VC goes to zero, this would be called a traffic jam. And then this equation that we just used makes no sense because there is no VC. For that case, use a different EF. EFC in units of milligram per car per hour instead of per kilometer. For that case, S equals EFC, a different EF, times NC times L. There's no VC then. But we are going to use this one up here because we're always going to be talking about normal operation, not a traffic jam. Remember, we had this room and then we had a source that was just sitting in one location. And that's what this is now. We have this tunnel and we just have some source, some capital S. But that's not what we want. The source is not at a point in the tunnel. It is distributed. And especially if we're trying to model this as a steady situation, we don't care about these individual cars. We just care about the fact that with X, there's some distributed source that's through the entire tunnel. So we want to somehow distribute that S through the whole tunnel. Here's how we're going to do that. Let's take a little control volume with some dimension dx. And instead of one source, we imagine a distributed source so that it's just a whole bunch of tiny little sources. And we're going to call that little s, capital S times dx over L. This little s is a uniformly distributed source. If you integrate from x equals 0 to L, this gives you capital S. And I'll do a quick example here. The air quality in an automobile tunnel is being analyzed. Carbon monoxide is of concern. And the tunnel has these specifications. Using the worst case scenario, predict the average source strength of all the cars combined in this tunnel. When I say worst case, we're going to use the bigger one that I gave you, which is the older one for older cars. And then capital S, and then just plug in the numbers. And we get S is 5.71 times 10 to the 7th milligrams per hour. 9.52 times 10 to the 5 milligram per minute.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.